ingenious innovation only proves its suitability in the industrial production process. 6 Fraunhofer institutes have succeeded in using digital printing and laser processes to individually integrate, for example, conductive paths and sensors and into components. The result? Completely new possibilities for construction and design, material savings, and the individualization of components in mass production environments. At first, it seems paradoxical to produce unique pieces in mass production. If, however, the digital manufacturing technologies of inkjet printing and laser processing are cleverly integrated into volume production environments, the products can be individualized in line. In this Lighthouse project, 6 excellent Fraunhofer institutes are working in project groups that together in their laboratories are already making the future of manufacturing technology tangible today. The demand for individualized components with sophisticated functionalities in industrial production is growing. By integrating digital printing and laser technologies into existing mass production environments, the new challenges can be easily mastered in the future. The creation of completely new products becomes possible. The development potential and the possibilities of industrial applications are almost unlimited. A central point is the transmission of electrical signals. Take automotive, for example. The control elements on the dashboard, the interior door lighting, or modern distance sensors. The new technology opens up possibilities for customizing body or interior components. At VW's Wolfsburg plant, for example, only 2 identical vehicles come off the production line each year. Each vehicle contains up to 8 kilometers of copper cable. This corresponds to a weight of about 160 kilograms. Previously, cable harnesses were assembled on laying boards and then laid by hand. This is cost-intensive and can now be a thing of the past. The Go Beyond 4.0 project has made a leap in production technology in this respect. The developments of Go Beyond 4.0 enable a complete rethinking in the construction of car body components, such as car doors. It's already possible today to produce conductive paths using printing and laser processes. First, a laser is used to make a trench in the metal surface of any 3-dimensional aluminium sheet for the conductor paths printed later. In a second step, an electrically insulating ink is printed into the lasered indentations. It's then cured using a laser process developed at Fraunhofer ILT. A dispenser then prints the conductive paths with an electrically conductive printing paste, which is then functionalized by a laser. Both steps are performed by a robot or a multi-axis system. The functionalization of the printed conductor paths by means of laser radiation enables local heating without heating or damaging the actual component. The print and laser heads will later be used by robots in a fully automated production line to add electrical functions to components. The robots can move in such a way that 3D components can be coated without any problems. The robot-guided inkjet printing process developed at Fraunhofer INAS allows even finer conductor paths with a minimum width of 50 micrometers to be printed. This enables the efficient production of a large number of parallel conductive tracks. As a result, the printed conductor paths are now part of the car door. The overall construction is lighter and more stable, and there's no need to install a wiring harness later. The technical challenges in this project were the selection of the optimal and most suitable functional ink and the high-precision surface pre-treatment in order to produce an exact print pattern. We use a special silver nanoparticle ink for the conductor paths. This is where our know-how in functional printing comes in. When larger currents are required, for example to supply small motors for side windows or tailgates, a different technology is used. Fraunhofer IWU has developed an innovative process that uses an industrial robot system to automatically apply copper wire lines with an insulating sheath directly onto the component. The robot is programmed according to the three-dimensional shape of the car door. To bring these processes into the production process, it's important that the individual steps of pre-treatment of printing and post-treatment are combined in one place. Here, the aim is to move components as little as possible, because they're large and difficult to realign. Optically transparent objects such as lenses that project lettering or logos can also be produced using digital printing and laser processes. Fraunhofer IOF's digital inkjet printing process can specifically generate phase differences in optical objects. The team from Jena uses an ink consisting of an optical hybrid polymer, Ormo-Cer, developed by Fraunhofer ISC in Würzburg, to create individualized optics. The optical properties of the material almost come close to those of good optical glasses and can be adapted to the respective application. In addition, conductor paths and LEDs can be integrated into the optical objects. Finally, a laser can generate defined absorption areas in order to control the shadowing of scattered radiation from LEDs. When particularly small and slim conductor paths have to be printed into optical objects, a further digital printing process, so-called aerosol jet printing, is used. Scientists at Fraunhofer INAS and IFEM have advanced the technology for this application. After the conductor paths have been manufactured, very small light-emitting diodes are placed using a pick-and-place process and thus hybrid integrated. The printed individualized optics are beam-shaping optics. That is, we can produce luminous elements such as lettering, logos, operating elements, or illuminating elements, for example, for building lighting. The combination of material properties and additive production enables us to address numerous scenarios as well as applications in the field of medical technology, automotive, and consumer goods. Researchers at IFAM in Bremen are showing just how diverse modern printing technology can be. Nowadays, printing means that smart elements can also be integrated into multi-layer components made of fiber-reinforced plastics. Aviation is a particular challenge due to its high safety requirements. In addition, the industry demands further weight reductions with increased intelligence of the components. Take the example of aircraft wings. For applications in aviation, a whole range of printable components such as temperature sensors, signal lines and contacts, wirelessly readable deformation sensors, capacitive sensors, or piezo impact sensors can be integrated into the wings. Heating structures, for example, can defrost wings without the use of chemicals. Thanks to various integrated sensors, the pilot is always informed about the current condition of his aircraft. This is important under mechanical loads on the fiber-reinforced structures, for example during hailstorms or in the event of mechanical damage during loading and unloading. To protect against external damage, the electrical functions printed directly on glass fiber or carbon fiber layers are infiltrated with epoxy resins in a vacuum infusion process and processed into fiber-reinforced plastics. Finally, the pastes are cured on the fabric in an oven or with a laser. The printed functions are now protected against external influences. With our integrated sensors, a pilot can continuously monitor the mechanical loads on a wing or fuselage structure. This is important in cases where a bird strike or hailstones after a thunderstorm cause mechanical damage. In addition, we're also considering equipping lightweight structures with our sensors, for example, in electromobility, or adding sensors to components in mechanical engineering. The reliability of the electrical functions produced by digital printing and laser processes is of particular importance. To ensure this, investigations are carried out, for example on a shaker that loads the components with a multiple of the acceleration due to gravity. This is because the functions produced, such as conductive traces with integrated LEDs, are intended to meet the high demands of the automotive and aviation industries. The increasing demand for individualization of industrial products calls for new manufacturing technologies. And this is why we at Fraunhofer are funding this topic as a pioneering lighthouse project in order to rapidly translate it into marketable products and expand the technological lead for the German and European economy. With digital printing and laser processes in mass production, volume products can be individually designed to save resources and be cost-efficient, right up to the unique specimen. Go beyond 4.0.